Classical physics at the start of the 20th century was defined by a massive structural divide. General relativity models reality as space-time geometry itself, while electromagnetism models it as a field that moves through that geometry. These two theories use different mathematical languages. Gravity relies on the metric tensor, g mu nu, a 4x4 matrix describing the shape of space. Electromagnetism relies on the four-potential vector, a mu, describing the direction of a field. In a four-dimensional universe, these objects cannot merge. A vector field cannot be folded into a geometric matrix without breaking the internal logic of the geometry. To achieve unification, a vector field must be forced to behave as an intrinsic property of the universe's shape. In 1919, Theodor Kaluza wrote to Albert Einstein with a radical solution. He proposed that electromagnetism is not a separate force at all, but simply gravity operating in a hidden dimension. Kaluza expanded this standard coordinate system, taking the four values of spacetime, x0 through x3, and appending a strictly spatial fifth coordinate, x5. By constructing a metric in this five-dimensional space, Maxwell's equations of electromagnetism emerge naturally from the geometry of a vacuum. We are going to build this model to see why the math is so compelling, and then calculate exactly where it collapses under the weight of quantum reality, creating the gap that necessitated string theory. We begin with Kaluza's five-dimensional metric tensor, hat GAB. Since our indices run from 0 to 4, the frame expands into a 5x5 matrix. In the upper left 4x4 block, we place the standard gravitational metric of our four-dimensional world. Kaluza used the new edges of the matrix, the outer column and row, to house the electromagnetic four-potential vector, a mu. This leaves one remaining gap in the bottom right corner. Kaluza assigned this to an unknown scalar field, phi. In this single matrix, gravity, electromagnetism, and a scalar field are now unified as a single geometric object. If a hidden fifth spatial dimension exists, we must explain exactly why we never see objects move through it. Kaluza bypasses this with the cylinder condition. He assumes that the derivative of any field with respect to the fifth coordinate is exactly 0. This restriction ensures that no physical quantity changes as you move along the fifth axis. Dynamics in that direction are frozen. The cylinder condition is a mathematical hack. It treats the fifth dimension not as a dynamic space, but as a rigid, static track. Even with that restriction, we can run this 5x5 metric through the machinery of general relativity to calculate the five-dimensional Ricci scalar, at r. This produces the Kaluza miracle. The five-dimensional action organically splits into two distinct parts. One term is the Einstein action for four-dimensional gravity. The other is the Maxwell Lagrangian for electromagnetism. Einstein presented this to the Prussian Academy because it achieved unification through geometry alone, without needing to add matter to the five-dimensional universe. It suggests that what we perceive as electromagnetic radiation is actually just the curvature of empty five-dimensional space. In 1926, Oskar Klein attempted to give Kaluza's cylinder condition a physical basis through a process called compactification. Klein proposed the fifth dimension is physically curled into a microscopic circle at every coordinate in our four-dimensional space. Because this space is a closed loop, momentum moving along it must be strictly quantized. Physical waves must form stable standing waves to exist at all. In this model, a gauge transformation, the symmetry that defines electromagnetism, is actually a physical displacement around this tiny circle. This means what we measure as charge is simply the quantized momentum of a particle spinning in that hidden dimension. This geometry predicts an infinite tower of massive particles called Kaluza-Klein modes. The mass of these particles is determined by this equation, where mass is inversely proportional to the radius of the compactified circle. If we look at the first excited state, n equals 1, we should find the lightest charged particle, the electron. To stay hidden, the fifth dimension's radius must approach the Planck length. Plugging that in, the equation violently predicts a mass of 10 to the 19th giga-electron volts. An electron's actual mass is 0.5 mega-electron volts. The prediction is off by 20 orders of magnitude. The theory has other failures. It requires a scalar field, phi, that has never been observed. And a single extra dimension only provides U1 symmetry, unable to account for nuclear forces. Physics eventually moved past Kaluza Klein, prioritizing the empirical accuracy of the Standard Model over five-dimensional geometry. But the core idea survived, that the fundamental forces we see are manifestations of the geometry of hidden, compactified dimensions. This structural insight became the basis for 10-dimensional string theory.